Somewhere in our galaxy right now, something invisible is tearing a star apart. It has no light, no surface, and no edge, and yet it is the most powerful object in the universe. We call it a black hole. And after a century of study, it still breaks almost everything we know about physics. Today, we're going inside one, from the edge of no return, to the very last second before you disappear forever. It starts with death. The death of a star, at least 20 times heavier than our sun. For millions of years, a star survives by fighting its own gravity. Fusion pushing outward, mass pulling inward. But once the fuel runs out, that fight ends instantly. And gravity wins. The outer layers blast into space as a supernova. But the core keeps collapsing, smaller and smaller and smaller, until all that mass, sometimes more than our entire sun, is crushed into a single point with zero volume. That point is called a singularity, and the gravity around it is so extreme, it bends space itself. Around it forms a boundary called the event horizon, the edge of the black hole itself. Cross that line, and no signal, no light, no information can ever come back out. Not even to warn you. That's why it's called black. It isn't a hole in space. It's a trap made of gravity so strong that light itself can't escape. And this is just the beginning. Because what happens near that edge is stranger than anything science fiction ever imagined. Imagine flying a spacecraft toward a black hole. At first, nothing seems unusual at all. From a distance, gravity behaves exactly like Newton described it centuries ago. But get closer, and space starts playing tricks. Light from behind the black hole bends completely around it, at a precise distance called the photon sphere. Light can actually orbit the black hole in a perfect circle, forever. This is why images of black holes show a glowing ring. You're not just seeing light beside it, you're seeing light bent from behind it. Keep going, and you reach the event horizon itself, the true point of no return. From the outside, something falling in appears to slow down and freeze, forever fading, never quite crossing the line. But from its own point of view, it crosses instantly. Time itself behaves differently depending on where you're standing. This is Einstein's relativity in its rawest form. Gravity doesn't just pull, it reshapes time and space together. And once you're past that edge, every possible path, every direction you could ever move, leads only one way. Inward. There is no reverse thrust powerful enough. No trick of physics that saves you. This is the last stop before the unknown. If you fell into a small black hole feet first, physics has a name for what happens to you. Spaghettification. It sounds absurd, but it's real. Gravity pulls harder on whatever part of you is closer to the black hole. Your feet would accelerate faster than your head, and the difference, the tidal force, would stretch you like taffy. Around a small black hole, this happens long before you even reach the edge. You'd be torn apart at the atomic level. But here's the twist. Around a supermassive black hole, millions of times heavier, the math flips completely. The gravity gradient is so gentle that you could cross the event horizon of a giant black hole and feel almost nothing at all. No pain, no warning sign, just silence, darkness, and a boundary you'd never even notice you crossed, until you looked back and realized every possible path home had already disappeared. From there, the pull only grows. Space itself begins flowing inward faster than light can escape it. And at the very center, all of that falling matter, everything you were, gets crushed into the singularity itself. What happens after that? No equation we have today can actually answer. Not every black hole is the same. In fact, they come in 4 very different sizes. Stellar black holes are the most common, born from single collapsing stars, roughly 5 to 20 times our sun's mass. Our galaxy alone may hold 100 million of them quietly drifting through the dark. Then there are intermediate black holes, a missing piece scientists only recently confirmed exists at all. At the center of nearly every galaxy sits something far larger, a supermassive black hole, millions or billions of times our sun's mass. Ours is called Sagittarius A star. It's over 4 million times heavier than the sun, and it's been there the whole time. We know it's there because nearby stars orbited at speeds that should be physically impossible near anything else. And then there's the strangest category of all, primordial black holes, possibly formed in the first second after the Big Bang. Some may be smaller than an atom, yet weigh as much as a mountain. We've never confirmed one exists, but we haven't ruled it out. From atom-sized relics of the Big Bang to monsters billions of times our sun's mass. Size, it turns out, is where the differences only begin. Because when a black hole starts actively feeding, it becomes the brightest object in the entire universe. Meet the quasar, a feeding supermassive black hole so bright it can outshine every star in its galaxy combined. As gas and dust spiral toward a black hole, they don't fall in quietly. They collide, compress, and heat up violently. This swirling disk of superheated material, the accretion disk, can reach temperatures of millions of degrees. Some of that energy escapes as jets, beams of particles blasted out at nearly the speed of light for thousands of light years. This is a quasar, and in the early universe they were some of the most powerful objects that ever existed. Even our own galaxy's black hole occasionally flares. A sudden burst of light from matter falling in, right now, tonight. Not everything that gets close falls in cleanly, either. Some material orbits chaotically before finally crossing the edge. Sometimes, an entire star wanders too close and gets shredded into a bright, glowing streak, feeding the black hole for months. The light from some of these ancient quasars has been traveling toward us for over 13 billion years. Which means, when we study them, we're not just looking at a black hole, we're looking directly into the deep past. And in 2019, one of those distant monsters gave us something no one had ever seen before. For a century, black holes were pure theory, mathematics no one could actually see. Then, in 2019, that changed. Scientists linked 8 radio telescopes across the entire planet into one virtual telescope the size of Earth itself. It was called the Event Horizon Telescope. Its target, a supermassive black hole 55 million light-years away, in the galaxy M87. After 2 years of processing unimaginable amounts of data, this was the result. The first photograph of a black hole in human history. That ring isn't the black hole itself. It's the photon sphere, the light bent completely around it. The dark center is the shadow of the event horizon. 3 years later, the same team turned their instrument on our own galaxy's black hole, Sagittarius A star, and succeeded again. Because it's so much smaller, imaging it was even harder, like photographing a single grain of sand from across the planet. 2 black holes, 2 photographs, and for the first time, undeniable direct visual proof that these monsters are real. But here's the part almost no one expects. Black holes don't actually last forever. In the 1970s, physicist Stephen Hawking made a discovery that shocked the entire scientific world. At the quantum level, empty space isn't truly empty. Pairs of particles constantly flicker in and out of existence. Right at the edge of a black hole, sometimes one particle falls in, and its partner escapes into space instead. From the outside, it looks like the black hole itself is emitting particles. We call this Hawking radiation. Every time this happens, the black hole loses a tiny amount of mass. Over unimaginable spans of time, it shrinks. For a black hole the mass of our sun, that process would take about 10 to the power of 67 years to finish. That's trillions of times longer than the current age of the universe. But eventually, it ends in one final burst of energy. Some physicists believe that in the unimaginably distant future, black holes will be the very last things left in existence. Despite everything we've learned, the center of a black hole still breaks physics completely. At the singularity, our equations for gravity and quantum mechanics both stop working. They simply give us infinity. Reconciling those two theories into one complete explanation remains one of the biggest unsolved problems in all of physics. Some scientists theorize black holes could even connect to wormholes, theoretical shortcuts through space and time itself. Others propose the mathematical opposite, a white hole, which would only ever expel matter and never pull it in. None have ever been observed. There's also the information paradox, the question of whether everything that falls into a black hole is truly lost forever or somehow preserved. A century after Einstein first predicted them, black holes remain the closest thing science has to genuine, unsolved magic. And somewhere out there, one of them is growing larger. Right now, as you watch this. If this blew your mind, subscribe, because we're just getting started.